Welcome back, pre-calculus students. So we are now entering what can be actually seen as the second half of the course, since pre-calculus is really divided into two parts, algebra and functions. So today, introduction to functions. I think everybody knows what the function is. I'm not going to insult you by defining a function, but if you wanted to know verbally what is a function, it's an operator that takes an x value and somehow transforms it into a y value. So the notation that we all know is the following. We say y is equal to f of x. Right? So that means that y is a function of x. An example of a function, well, we have seen many functions in high school, yes. For example, y equals x squared. That's a function that takes an x, squares it, and the square of x becomes what we call y. Another one, y equals x over x plus 1. This is a rational function. If you enter an x here, well, you do this operation and you will obtain a y, and so on and so forth. We will study several types of functions since calculus is really based on functions. One of the main things that actually we need to be worried about functions is their domain. So let me talk for a moment briefly about the domain of a function. So domain of f of x. What is that? What is the domain? Do you know what the domain is? Anybody recalls? Domain? It's the set of what? X values. Yes. X values that can be replaced into the function. That can be replaced into f of x. Okay, so that suggests that potentially we are not able to replace any x we want into a function. There might be functions that have what we call a restricted domain. Let's take a look at that. So example 1. Let f of x equals x squared minus x plus 1. What would be the domain of such a function? Domain? What is the domain of such a function? What do you say? Domain is the set of x values that can be replaced in here. Can I put negative x's in there? For example, can I put, I don't know, minus 2? Would that be possible? Would I get a y value? Well, I would get minus 2 squared minus 2 plus 1. So that's equal to what? 4 plus 2 is 6 plus 1 is 7. Yeah, that is totally a number, right? So can I replace perhaps, what other weird numbers do we know? 0 maybe? Can I replace 0 in? What is f of 0? Well, 0 squared minus 0 plus 1, that's equal to 1, and that's a number. So I can replace negative number, I can replace positive numbers. Can I replace, say, x by 1? Would that work, or would I get something that is crazy? What is f of 1? Well, it's 1 squared minus 1 plus 1. That is also equal to 1. Everything here seems to work out. I can't seem to be able to find a value that I would not get a y value for if I replace the x in. In this case, the domain is said to be R. Domain is every x value. And every x value we say is the set of all real numbers. This is the notation for the set of all real numbers. We could also write it this way: minus infinity to infinity with open ends at both minus and positive infinity. Right, so that looks like a bit of a tedious way to look at domain, yes? I don't disagree with you if you think that this is tedious. Let us actually take a look at a better way of doing this. So graphically, we can identify the domain of a function by using what is called the vertical line test. So the vertical line test allows to determine the domain. Allows to determine the domain. For example, suppose I have y, or f of x, same thing, y and f of x, same thing. Y is equal to x squared plus 1. The graph of this, we all know. What does it look like? The graph of f of x equals x squared plus 1? Well, x squared is a parabola, and plus 1 basically lifts it up by 1 unit. This is actually equal to 1. Notice that this parabola extends its arms both ways like that. There is no ending to this. The vertical line test is as such. If I draw a vertical line here, do I cross the graph? Yes, right here. If I draw another vertical line here, do I cross the graph? Yes, right here. And so on, and so forth. Every time I draw a vertical line, I actually hit the graph of f of x. That determines that the domain of this function is everything, right? There is no place where I can draw a vertical line where I'm not going to cut the graph. So I can actually say that, again, the domain of this function is R. Right? If I give this to you, so the graph of f of x, graph of f of x is this. I should label my axes, x, x, y, 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 y. Suppose I give you a graph that looks like this. All right, so I'm not giving you like a definition of, analytical definition of what f of x is, but I am giving you its graph. Let us say that this corresponds to the point 2, and this other point corresponds to, let's say, 5. What is the domain of this function? Well, if I use the vertical line test, here I cross the graph. And I would continue crossing the graph since this goes on forever. Here, I cross the graph. I cross the graph right here. Now, would I cross the graph at 2? Oh, no, because there is an open dot at 2. So 2 would actually be excluded from the domain. Same thing for a line that would actually go through here. At 5, I would actually not cross the graph because at 5 I seem to have, according to the graph, a vertical asymptote. So what would be the domain of this function? What would be the domain of this function? It would be every real number except, so we write it this way, slash, except two values. Which two values shall be excluded from my domain? The value of 2, because the vertical line here doesn't strike the graph, and the value of 5 for the same reason. So except 2 and 5. That's how you may actually determine the domain of a function graphically. Now, how do we determine the domain analytically? Well, let's consider yet again another example. So example 4. Consider f of x equals to, what shall we have? Let's take a root. The root of 1 plus x. Okay? So, why don't we take a look at this graphically speaking? The graph of this we have actually looked at before in high school. We can revisit now by taking a couple of values. For example, let's say -2, -1, 0, 1, 2. So this is one way to sketch the graph of a function. You take a table of values and you put them in. 1 plus -2 is -1. Uh-oh, the root of -1, no such value, empty set. -1 plus 1, 0, root of 0. Okay, we got a value here. 0 plus 1 is 1, root of 1 is 1. 1 plus 1 is 2, root 2. 2 plus 1 is 3, root 3. So graphically speaking, what do I get? -1, 0, 0, 1, 1. Root 2, root 2 is what? 1.4 ballpark. So if we put 2 here, we're going to get something like this. And then 2, root 3, a little bit more like that. And if you join the points, you're going to recognize the old high school shape of a square root, right? So conducting the vertical line test on this means as follows. Vertical line here, am I cutting the graph? Nope, there's no graph there. Is there any graph here? Nope. Nope. I'm only starting to cut the graph when x is -1. And then I cut the graph here, and then wherever I draw, I cut the graph, I'll be cutting the graph forever as I go to the right side. So the domain does not begin until we have -1. This actually says that the domain is, how do I write this? From 1 to infinity. So I can say from 1 to infinity. Now infinity is never included, so it always carries an open bracket. Good. Now, what if I don't want to draw the graph? What if I want to actually be analytical about this? I can see that I have a square root in this function. Now what do we know? Square roots cannot be negative, as we have shown here. When you plug in -2, 1 plus -2 is -1, and the root of -1 does not exist. We all know that. So basically, when we have a root, when we have a square root, should I say, we need, what do we need when we have a square root for things to work in terms of x values? We need the x values to be in a certain way such that the inside of the root is never negative, right? We need the inside of the root to be always what? Positive, right? So, if the inside of the root is to be positive, and I have y equals root of 1 plus x, what is the inside of the root for this guy? Well, it's right here, isn't it? That's the inside of the square root. So I will translate this now. The inside of the square root must be positive. So i.e., conclusion, 1 plus x must be positive. And what's another way to write 1 plus x must be positive? Well, 1 plus x must be greater than or equal to 0, right? If you're positive, you're greater than or equal to 0. So that means that x is greater than or equal to -1. And, of course, that is exactly the same domain as we had found using the vertical line test. Except that this is probably shorter in terms of work. Don't need to sketch the graph for that. Yes? So, what do we learn here? If we have a square root and we're interested in finding the domain of the function, make sure that the inside of the square root turns out to be positive. Okay, good. All right, so example 5. Example 5. This time, consider f of x equals to, what could we take? Something that we encounter in calculus very, very much. A rational function sound like a good idea. 1 over x minus 2. So, as we did before, let's take a look at this graphically. Graphically. What is the graph of a rational function? Well, if we remember, it's a good thing. If we don't, table of values. All right, -2, -1, 0, 1, 2, and 3, and 4. I need a few more values here to get a more precise graph. So, -2 in there. What is f of -2? That's basically replacing x by -2, so that's going to be -1/4. -1, it's going to be -1/3. 0 minus 2 is -2, that's going to be -1/2. 1 is going to be -1. 2 is going to be a very interesting animal. 2 minus 2 is 0. I'm getting here 1 over 0. Does that exist? 1 over 0 does not exist. Very interesting. We're going to see what corresponds to that on a graph in a minute. What about 3? 1 over 3 minus 2, that's 1 over 1. 4 minus 2 is 2, so 1 over 2. I think we have enough values here to get a pretty good idea of what this graph may look like. So, y-axis, x-axis. Okay, -2, -1, -2, 1, 2, 3, and 4. Let's plot these points on the Cartesian plane. Here, let's have here what? -1, and here 1. So -2 -1/4, wow, very close to the x-axis. -1 -1/3, slightly higher, but not that much. 0 -1/2. 0, I'm sorry, I put that above the x-axis when it should be below, my bad. -2 -1/4, let's put it here. -2 -1/4. And -1 -1/3, a little lower. 0 -1/2, that's still a little too high. So here, then 0 -1/2, we said roughly here. I can bring this down a little bit for the sake of having a better scale. So let's have -1 here. What else? 1 -1 would be here. And then so far, what do I have? I seem to have something like, whoa, something like this, something plunging like that, because at 2, precisely at 2, I have something that does not exist, and soon we're going to see that this corresponds to something that you've seen in high school. This is a vertical asymptote. So my graph should actually lean more like this because it's a vertical asymptote. Now what happens on the other side? 3, 1, and then 4, 1/2. We can see that we're going to have exactly the reverse shape here. It's going to look like this. I'm sorry if my hand is not very, very steady. And then we have a very recognizable shape, which is called a rational function. We've seen that plentiful in high school. And it's got kind of a shape like this. It's not the best graph I've ever done, but I think you get the idea. So if we do the vertical line test on this, right here, it's going to cross. It's going to hit. It's going to touch. It's going to come across. It's going to come across. Kind of everywhere, including on the right side, right? The vertical line always crosses the graph except at one value, and that value is right here at 2, right here. So if I plug in 2, 2 minus 2, 0, 1 over 0 does not exist. That's the value that is excluded from the domain because the vertical line test does not cross the graph at 2. Ha! So, conclusion. The domain of this function is everything, right? My vertical line will cross everywhere but at 2. So domain is everything, we say R, except the value, what? 2. That's right. Good. So that's how you would do it graphically. Now, analytically, how would I actually tackle this problem, say, without sketching the graph, without the table of value? Well, what is wrong with this graph in terms of domain? There's a vertical asymptote. Now, where does that vertical asymptote happen? It happens when x is 2. And that value, I know many of you have noticed that already, that value 2 is exactly the value that made this denominator equal to 0. Yes? If I plug in 2 minus 2 in the denominator, we've seen we're going to get 1 over 0. Ha! So, analytically, the denominator of my f of x cannot be 0. I'm going to write it this way. Denominator cannot be 0. What's my denominator here? X minus 2. The numerator is 1. The denominator is x minus 2. So x minus 2 cannot be 0. That means that x cannot be 2. And that's exactly the same thing as saying the domain of the function is everything but 2. Except that this is a million times faster, isn't it? Right? So what have we learned in the past two examples, example 4 and example 5? Let's summarize this before we do the next example. In example 4, we had a root, and we said the inside of the root cannot be negative. Yeah? In example 5, we had a rational function with a denominator, and we said the denominator cannot be equal to 0. These are going to be the two conditions that I got to keep in mind when I search for the domain of a function. So let's summarize this a little. So how does that go? Summary of what we have learned so far. When looking for the domain of f of x, when looking for the domain of f of x, be mindful of the two following situations. So when looking for the domain of f of x, be mindful of the following. First, if you have a square root, if you have a square root, I'm going to put the 2 here to emphasize that basically there's a square root. Now this square root will come with an inside. Okay? Now, if you have a square root and you have an inside, make sure that the inside, is what? Is positive. Make sure that the inside is positive, which means greater than 0. This will give you an inequality that should not be very difficult to solve. And that's going to give you your domain. Now, suppose you don't have a root, but you have a rational function. If you have a fraction of the type something, let's put just 1 for the sake of the argument, because what matters here is not the numerator, but the denominator. Let me call it the bottom of the fraction. Then make sure that the bottom of the function, is actually what? What can the bottom be? Well, it can be a lot of things, but it cannot be 0. That's for sure. Okay? So these are the 2 main things that we have to be concerned with when we talk about the domain of a function. Let's take a look at an example. Okay, suppose I have, this would be what, example 6, I guess. Find the domain of f of x equals the following. 1 over the root of 4 minus 6x. So that is f of x is equal to 1 over the root of 4 minus 6x. I chose this example, which we can probably label what? 2.5 stars if you keep track of this sort of thing. I chose this example because it has, in the same problem, my 2 situations. It has a bottom and it has a root. So I got to be mindful of both of these things at the same time. So first, inside of the root, so I have a root with an inside in this example 6, and that means that we need the inside to be greater than or equal to 0. Inside greater than or, and I'm going to put the equal here in green because I will want to discuss this with you in a moment. So inside greater than or equal to 0. That's in general what we do when we have a root, right? Now, my inside is 4 minus 6x greater than or equal, yet again in green because this is subject to change, 0. So that's 4 greater than or equal to 6x. You know what I've done here. I have switched 6x to the other side. And that means that 4 over 6 is greater than or equal to x, which is the same thing as 2/3. 2/3 greater than or equal to x. That seems to be my domain, because any value that are less than or equal to 2/3, you can also write this backwards, x less than or equal to 2/3, same thing. Okay, So that seems to be the domain of my function because I basically took care of the inside of the root, and then it should be this, right? Mais attention here, and that's why I put the greater or the less than in terms of a green thing. I can't have the denominator 0. So I have 1 over a bottom, but I do not want the bottom to be 0. So here, the bottom cannot be 0. So that means that my root cannot be 0. So what does that mean? It means that the root of 4 minus 6x cannot be equal to 0. Squaring both sides, 4 minus 6x cannot be 0. And then the solving of this will resemble the solving of that. We're going to get that x is actually not equal to 2/3. Now what does that do? It actually wipes away the equality in my inequalities. So that means that the domain, so conclusion, where do I put this over here? Conclusion, the domain of this function is 2/3, so less than, so infinity, 2/3, no, sorry, that's wrong. So it's less than 2/3, so it's 2/3 over here and minus infinity there. Open, and then at 2/3 I have to open the bracket because the 2/3 value is not included in the domain as we have seen here, simply because it makes the bottom 0. Okay, enough on this for the moment. We shall revisit the issue of functions. We are only starting our study of this. We'll see some more in the next video. In the meantime, take care of yourself. I will see you soon.